Okay, let's see. There's a number of other things we still have to do. Let's start out with something fun. We can improve the tutorial. So we just made a change where for the dash dash charge neutral feature in Bentopy Solvate, and we should consider also changing that in the tutorial. So I here have my local copy of, let's see, what is it? My local copy of the Bentopy tutorial. Now we can start to update it so that it actually matches properly. So if we now grab for this little thing, we find that, and now we can go to the index.qmd for charge auto. I think actually we should put this here. That's better. Cool. I like that. Let's view it now. If it works. What happened? Oh, I'm already looking at it somewhere else. Where? I'm trying to find it. There it is. Let me quickly find a cool way to show this. I might as well go here. Right. So more tweaks we can make. Kind of depends on. I mean, I have a whole to-do list actually. It would actually be interesting to maybe quickly execute on this tutorial to make everything. Yeah, let's do that. So what I'll do quickly, create something so I don't know where I'm at, and then we need to make this a bit small, not too small, of course. Like this. We open up a terminal. And now we can make a new directory. Let's go just to a temp. Okay, let's follow the directions. So I could do this. First, let's make a venv actually. I could do this with install Bentopy, but then we get an older version. We actually want the very, very latest version because that's where the updates I want to introduce are actually located. There we are. That doesn't work like that. This is what we should do. Wait, don't do that. No, whatever. Yeah, perfect. So now we have a bunch of tutorial files, which are MDP files, structures, and a topology, and the structures and topology contain this stuff. This is in the MDP files. Maybe make a bit bigger. So you have a ubiquitin ITP and a lysozyme ITP. We have the Martini 3 force field that we need. We have a membrane and a double membrane. We have our lysozyme and our ubiquitin structure. We have a water structure that we don't need anymore. So yeah, and all of these other things we have. So now let's consider that we want to make a space, just a box, and completely fill it with something. No interesting geometry or topology to the box, just a plain box. So in order to do that, we first create a Bent file. Now a Bent file contains all of the information that you need in order to pack something. So we're going to put in this file. So let's create simple packing.bent. I've done this many times before, obviously, because I'm testing the tutorial. And we can put the seed to 0 to make it deterministic across different runs. Not strictly necessary, and also the seed is also printed to the output file, but whatever. I think it's generally good practice. So we make our dimensions is 40 by 40 by 40 nanometers, and then our resolution is 0.5 nanometers. And we make our includes. So this will end up in the top file. This is super helpful because it helps you actually properly manage the topology for your system, all in an integrated way. So we can copy these. I like to type it all out because then I'm also encountering any paper cuts that may arise when you actually try to type it yourself. So here we say system is all. So here system is actually the name of our compartment, and all is all that says that we take the whole space. Okay, and then we place our segments. So segments are the things you place, right? You can have a single structure, but then place it many times at many different concentrations in different locations. Each of those different kind of placing groups is a segment in our vocabulary. So we call it lys, which matches the ITP file. I can quickly show you topology lysozyme ITP. So here, this is molecule type. And yeah, so we need to match that name here if we want it to make sense as a topology. And then we take it from structures lysozyme.pdb, and we place it in system, right? This is the same name as we made before. So now we can say Bentopy back. Let's confirm, yeah, I have the correct version. Simple packing.bent, and I like to make a placement .json. Yeah, exactly. And then we can also render it, because now if we would look at the placements.json in an editor, you see this whole mess. This is actually just JSON, nothing to be afraid of. right? So we can just inspect it like this. And what you see is it includes this and it includes a lot of other information, including all of the rotation and position translations, all of the orientations for all of the different instances. Instead of all of the coordinates, you just have an instance-based system here. So then let's see. Here's an interesting mistake already that we'll deal with later. Or maybe I need to refresh. I don't know. Yeah, we'll deal with this thing in a moment. Yeah, so now if we do Bentopy render, we create system.grow and then we also make a topology. Yeah, so now if we look at the topology, it's very reasonable. It's just exactly what we wanted to put in, right? And all of these includes have been placed here. Now we can actually start looking at our system.grow. So that's very pleasant. Oh gosh, it's running VMD2, which I'm not too keen on. I mean, we can try and figure it out. There we are. That's much better. So here we see all of our lysozymes. That's excellent. We'll quickly fix up some things though. There we are again. I think I fixed the issue with VMD that I did not like. Hey, anyway, we're going to try and see whether VMD2 works for us here. It should be generally the same. Yeah, so what I see here is that the compensatory charge that we need to deal with is like this, but now we actually have access to the neutral option. Yeah, I'm so sorry about this shitty layouting here. Yeah, that's not going to work. Just don't have too much room here. Maybe from time to time we can actually move this out of the way. Yeah, like this. This is much better. So here, yeah, let's actually put this at kind of designing, right? This is now something we're able to say, except we do need a topology, so it will complain. So we provide a topology like we had, but I prefer it to be here, I guess. Yeah, that's great. So now it creates a topology and it reads the number of sodiums it needs to compensate still. And here the total system charge is positive 5,200, and that is getting compensated with additional chlorides. Yeah, so we end up having that nicely here. And now we can also look at the system again. Let's see whether our changes to the VMD config help. So let's take a look at this. That doesn't seem too good, but the thing is we're actually not looking at the solvated system. What did we write? Solvated. Oh, solvated system.grow. All right. There we are. So now if we look at it, you see that it's like a whole block of water, and you see all of these differently colored beads there. And it's a whole periodic box, right? So you see these cutouts, and then here you see these protrusions, but they match up. And it would be nice maybe to cut it open, so we can say something like this. Yeah, that all looks pretty neat. Excellent. Then let's go to the next step. So this is something we need to change actually. Yeah, so now I'm getting confused because I actually can't find it in the tutorial here anymore, even though it's definitely something we just saw. Yeah, I actually fixed it here. Oh, and now I also remember why I did this, because then that shows up nicely. Yeah, that's a bit frustrating. Why am I not seeing it over here? Quickly restart the Quarto run that's going on. I don't trust it anymore. There we are, that's perfect. So now we can test this properly. Yeah, it appears to be doing a good job, except now the charge is 0. Why is that? Well, we're appending to the same topology, right? So if we remove this, then it's just like before. It's like it keeps appending, it keeps appending. It's something to be aware of. Maybe at some point we'll actually do something like an input topology and output topology, while also retaining the appendability. I mean, in reality, append is great, right? If you don't run it many times in succession, which you would normally never really do, it's fine. Here's something fun we could try. So we can look at our simple packing thing, and then we put in these compartments where we say, hey, instead of everything, we conceptualize this compartment called system as a sphere at the center coordinate. We can also put in an actual coordinate, but with a radius of 20 nanometers. And then likely we will not fit all of these lysozymes in there because it's just too tight. Don't know what happened there, but oh, yeah, it's disappearing. I sure hope that this works. Hello. There we are. Remove the typo. Now if you Bentopy render this thing again, then we get quite a different result. Now we put it into a sphere. See? That's pretty good. You can even do the same for a cuboid. Won't do that right now, because I know it works. This is something to keep in mind. I think I don't format that very nicely there. Yeah, so this should just become default. I'm a bit lost. Where am I? Yeah, that's much better. All right. Next step. It's gotten a little dark. Yeah. Next step is to learn about masking. So now we have a really nice newer rendition of the mask subcommand, which I will show you. Yeah, so we can look maybe first at the structures and then the membrane.grow. This is just a simple lipid bilayer. I think it's just POPC. And yeah, it's just POPC. And we want to kind of distinguish this membrane itself from what lies outside of it. So let's go, and then we can take this as an input, the membrane.grow, and we want to look at how Bentopy mask, which is able to distinguish different spaces through a really cool technique, which is also available as a library that we end up using here, right? It's created by Bart, and that's called MDV containment. And what it allows you to do is to not only distinguish different connected components, but also how they relate to each other in a containment hierarchy, which is a very powerful tool. We'll use it a little bit here, but not nearly all of what it can do. But yeah, we want to look at the labels that it creates. So we can create a labels.grow. So now it's loading the structure. Oh yeah, and we need to provide the closing flag. I think I'll make this default, but yeah, this is much better. So now we can look at the labels that were created. See this? So that's very reminiscent of our earlier membrane. In fact, we can even load the membrane real quick. So if we now look at the membrane, maybe we can present it as van der Waals spheres, which are terribly small in this case. I mean, we're dealing with Martini structures, so they need to be a bit bigger. That's much better. So now, if we look at them at the same time, maybe we can even cut away a bunch here. See what I mean? So it very nicely tracks with where the membrane actually is, and that allows us to distinguish these two spaces. So this one is called -1, and this steel space here is called 1. So now we know what to select. So we'll run the command again, but instead of visualizing the labels, we just provide -- label, or for short -l, and we call it membrane mask.mpz. I think this also, yeah, this is exactly what's described there. Then we can now set up a new packing file, so let's just copy that for now. So what you can see is that we import this newly created mask file, and then we create basically this solvent region by taking the inverse of it. So here we call it membrane, and then we do this not membrane operation in this, like, so you can say the name of the compartment you want to create, then a keyword describing what you want to do. So you want to do the combined rules, and then you want to have the inverse of the membrane. Then we create a neighborhood around it. So the interesting thing you can do is that you place, for example, one molecule everywhere except the membrane, and the other you place everywhere except the membrane, and also within some distance of the membrane. So here we create a space that is within 5 nanometers of the membrane, but that also includes the membrane itself. So then the actual space close to the membrane is a combination of the solvent, so everything that's not the membrane, and the membrane neighborhood. And then we place 300 lysozymes generally, and we also place 100, especially close, within 5 nanometers of the membrane. That's very cool. Then we can do Bentopy pack, membrane packing, write that out, so that packs very nicely, and then we render that out. And if we now look at the topology, then we see that it's now 300 lysozymes and 100 ubiquitins. Not the membrane though. we'd have to merge that. So now we can add we can merge the systems. So we can call Bentopy merge packed proteins, just what we made, and then or is that what we made? I think here we should say, yeah, exactly. So here we name the thing a bit differently because we want to emphasize the difference between the proteins that we packed in the membrane. So we create packed proteins.grow, and we also we append it to topology, or append it rather, we create a new topology that contains that stuff, and then we merge them. So we Bentopy merge the packed proteins and the structures membrane.grow, create system.grow from that. And then we can finally echo POPC, whatever this number is. This happens to be the topology of the membrane, which you would know if you had made the membrane yourself. So we append that to the topology. So now if we look at the topology, we get this nice result with the lipids there as well. Then we can solvate the system. Let's just copy that. There we are. And now we can take a look. So the solvated system.grow is what we're interested in. There we are. Oh, that's so cool. So now you see in green the water, classic martini water. So that's because VMD thinks our water is tungsten, obviously. Let's cut open, let's say, yeah, let's just remove everything that's not water or solvent. So we remove W, Na, and Cl. Okay, that's really nice, but now I don't really know whether our placement according to whether it's close to the membrane or not really worked. So we want to color differently the different parts of the system. So maybe we can do it positively. We say res name POPC, so that should be our membrane. Then we copy that one, and then we make res name lyse. Or do we? What is it called? That's it. We can give that a nice color. Maybe just like in the tutorial itself, I think we make the lysozyme green. Or a nice lime, I think. And then the ubiquitins, we make blue or cyan. So that's pretty cool. That worked perfectly. Very nice result. Now we're ready to move on to something where we actually need to distinguish two different compartments. So rather than just saying there is stuff here and there's not stuff here, we really want to say we have two membranes. Between those two membranes, we place this kind of thing. Between the other, or in the other space, we place the other two things. So let's do that. Yeah, so we can take a look at the double membrane real quick. There we are. So that's it. That's our double membrane. And we want to pack that full of stuff. So we then do a nice Bentopy mask. Run. So this is nice. There's a nice shorthand for the dash dash visualize labels, the dash B, and I like to use that. Yeah, we need to do closing again. This is definitely something we will take as a default because it's such a good feature. Kind of, if you have all of these little different compartments, you can kind of glob them together, right? So because we use a pretty small containment resolution of 0.5, so that's the same as we actually use for the packing. It can happen that all of the individual lipids, they're not very much connected in the eyes of MDV containment. And then by doing dash dash closing, you basically morph them to be a bit larger, and then you reduce that again, but that means that you form everywhere where things are very close, they will kind of bridge over. So that's excellent. That's really what you want here. And gives really, really good topologies. So what you can see is that we now have a -2 compartment and a -1 compartment. So the minus compartment is like empty space. And then the +1 and the +2 compartments are the two membranes. So you can also see how basically they all have the same number of voxels in them, which kind of makes sense. Here's something cool. You can also see their rank, and that says something about the number of dimensions in which it periodically spans the space. So that suggests something about the way that they're connected. So here we select the different compartments. Maybe we can color it like this. It kind of highlights how we're able to distinguish these different features. That's really nice. And now we can use that same command, but then use closing again, and then we describe that we want basically the mask for the A and the B space. So that's the different spaces that we found between the two masks, as well as the entire, like the set of membrane stuff, right? We don't care what membrane is what membrane, because we just don't want to place stuff there. So we want -1, we call that A mask dot npz, and then we want -2, we call that B mask dot npz, and then finally we take 1 and 2, so the solid components, call that membrane mask dot npz. Great, so now you can take this cool input file and we call it compartment packing.bent. So here things get interesting. We have our membrane that we want to avoid. Then we have our two positive spaces. But we also want to create a system where we have, maybe I can actually show it in VMD again. Basically what we want to create is a space where, let's see, we want ubiquitants here and here. And we want lysozyme all the way here and all the way here. So we want the ubiquitants to stay close to the membrane and only be in the inner compartment. And the lysozyme can be anywhere, but only in the kind of the outer compartment. Actually, calling them inner and outer is not correct here, because they both have the same rank and they don't include each other. One doesn't include the other. So they're basically equivalent in terms of topology or topological identity here. So that's why that's not entirely appropriate, and we use the naming convention or the name convention or just the naming scheme of A and B here. So we wrote those nice masks, and then what you can see in the input file here is that we import the membrane and the two different masks, and then the membrane neighborhood is within 4 nanometers of this membrane. And then within compartment B, so that's the one that appears for us, even though it's periodic, sandwich between the two membranes, we make a combination where it is both in B and also in the region of the membrane neighborhood. Okay, so now we understand that, and then we can finally get to packing. So let's Bentopy pack, compartment, packing, and we make some placements of JSON. And then here, we do the whole rendering thing again, like this. We've done that before. And we can also solvate just like before. And now we can simply look at our system. Yeah, so that's really cool. So now if we cut out the water, we can definitely see that it did place things, right, on the outside and on the inside in the way that I just described. But maybe we can be a bit more positivist again about what we include. It should be a res name. Should also be lysozyme. Let's color them again. So the lysozyme becomes lime, and the ubiquitin becomes cyan or blue or whatever. But now you can see that we actually managed to nicely match this figure here. So we did it. That's excellent. Yeah, so that is simply how we would go about doing that. And then if we also want to run a simulation of it, we can do that according to this. And this is kind of the process that you go through, right? Here you take your input structure in terms of like the membrane, for example, that you want to place around, and then you distinguish the two compartments, and then the packing process starts. So that, let's see whether I can zoom in on this. It will basically, in this kind of voxel space that we derive, it will start to try to make positions, and then when it notices that voxels overlap between, for example, this gray region and the green thing it wants to actually place, then it does not allow for that, and it's very easy and quick check to determine whether that's possible or not. And then it tries another position, and once that is accepted, then it will go for that and it will be happy. Then you do the same thing here, and there's some additional rules here actually for why the blue one ends up in this blue region, but also close to the membrane. And then we have that voxel space basically, but we also store this identity or this orientation for each of the placements. And because we store that, we can then go and render it in this instance-based manner. That's why there are different commands. It's very helpful. There are very different steps, right? The only thing that Bentopy pack remembers, and that's why it has a very low memory footprint as well, the thing it remembers is what rotation and translation it applied to get something there. And then finally for, you can use merge to integrate the components, and you can solvate it, and then we have a nice system that we can actually run in an empty simulation. And yeah, so that's pretty excellent. Okay, so I think the state of the tutorial is all right. I can probably update some of these figures actually. Had a meeting with Jan about that yesterday. Something I actually want to tweak. I mean, there's so many things I want to tweak, but it's in a pretty good spot right now. That's what I'm mostly very happy about. Okay. I need to go for a second, but I can pause the video, I think. Cool, so let's commit these changes real quick. We did what? Yeah, we removed that, I guess. Yeah, we moved that. Okay, let's be a bit more. This one we'll do unilaterally. Yeah, that can be a nice unilateral change that we make. Wait, this is not going well. So this one we don't do right now. This one we do. This one we don't. Here we need to split. This one we don't. This one we do. This one we do. This one we don't. This one we do. Don't. No. Yes. No. No. Yes. 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 Next. This movement of a figure we can do. Wait, that was not smart. There, that's the movement. Yeah, because now the whole thing is that we end up seeing this cool figure at the end. At first, I had put it here at the start, which I think is a little much. This is actually very helpful because it actually tells you what you're going to create. And then here, once you've learned a bunch of things, you can actually start to maybe look at what you learned in terms of this figure. That's the idea. But why does this only include whatever? We'll fix it. Yeah, there we are. More commits. So now we do the whole charge thing. Wait, what happened there actually? Yeah, that seems fine. Okay, finally, I think it's this details thing. And this might as well include this, so I don't know. Always forget that I'm actually working with JJ there as well, but you can use Git and JJ at the same time a little bit. It sometimes messes me up a little bit, but whatever. I like both. And yeah, now I'm contemplating where I want to work on those figures. Maybe I should. Let me quickly take a look. Okay, I'm kind of deciding against going with the whole change the figure slightly thing. I mean, I know where the source figures are that I could do that with. They're just updated in the sense, like if you actually compare this, for example, this is nice and thick lipids, where these are a bit spindly and small, for example, but it's really subtle. And actually, it's actually quite okay. Yeah, so I think that now is just a good time to maybe fetch some new changes from the fork. I just synced the fork in GitHub. There's no breaking stuff here, so now we can just git push our work. Yeah, what are we going to do actually? Yeah, I know, git or JJ. Oh no, are you running into issues? I don't know how this works yet. Know how to do this perfectly with Git, but then I really want to try JJ properly. And then I run into shit. But JJ git push. Ah, interesting. Yeah, so we want to be at RP. So JJ bookmark set main -r RP. That's good. There we are. Does it now show up? Yeah, there I am. Okay. Yeah, so you can see that I make many changes. Maybe that's a bit much. I can just rebase those, I guess. Or they all get rebased into the merge commit. That's kind of my point. Let's see whether I can actually open a pull request. That would be cool. How are people giving titles to their pull requests? Okay. We want to update it for the version that will be released basically now that it's being published. So update Bentopy tutorial to reflect recent changes with the Bentopy paper article being published very soon. We want to update the tutorial to match the current, to match the many wonderful changes we have made to the project since writing this tutorial. in the summer. Yeah, I want to draft it because there is some other changes I still want to do. Actually, now that I think of it, for example, the citation, how's that looking? I think we actually also know the page number now, which is conveniently. This can just be like this. Actually, we can literally copy it from our GitHub. GitHub is so slow. This is already the key I use in the document, so I'll change that. How does that show up? I mean, still correct, right? But, oh, this is probably something you need to restart Cardo for. That's a bit annoying. I think it should show the page number. Yeah, there we are. Perfect. Cool. Where am I? Yeah, excellent. So this will just maybe trickle through for a bit. There's more changes to be made, but let's see. Yeah, I want to reference the wiki, for example, fix the citation. Did that, did that, did that, did this. Yeah, that should work. Yeah, so that's another little change I want to make. I want to properly mention the really nice wiki that we have. Advanced. Just quickly copy the link. There we go. Do we want to mention it elsewhere? Pretty sure this is it. Yeah, that's it. Good. Okay, let's see. So I think for now, the smartest thing is to just cut a new release actually for Bentopy. So let's see, this we can close. Then yeah, basically we want to release a new version. And I think we need to really move to the 1.0 space already. So we're going to make a beta already. We're going to make beta 0 for the 1.0.0 version. So that's interesting. And I realize I think I need to source at least this building thing. Quickly drop that. Ah. Okay. Yes, we can pip install build. Should really figure something else out, but this is fine. I sure hope we have twine here, actually. Hopefully it didn't fuck something up. Let's build some wheels. It's a whole process. So now it's building the Linux pre-built binary wheels, which is really nice. And people don't need a Rust compiler to even build it. Yeah, and let's put it on test pipeline. Okay, and I think it's now time for a cool kind of integration test that we can make. Because our tutorial, in a way, serves like a nice test that at least needs to work, right? Kind of makes sense. So what if we take all of the parts that are within code blocks and then basically put that all in a document. So I'm thinking, let's just open a new buffer. That's where we'll put everything, and then we're just going to look for code fences. So we're going to install Bentopy. We'll look into that in a minute. Then we're going to install all of this. Then this we put into a file called simplepacking.bent. I don't know, quickly, in a minute, we'll deal with the bash bullshit, but I mean, And then we pack and we render. Then we can finally solve it. And we can look at the solvated system, but we're not actually going to do that. And we can change things around. Nah, let's not actually do that. That's a bit finicky. Okay, so this is section, or this is tutorial 2. Here we've had tutorial 1. Installation, repair working directory. I also say maybe we can make a temp there. Can do that like this, right? I mean, in Bash. Wait, what is it called? Temp. Oh, make temp. There we are. That's good. So we then go to our special working directory. We also actually want that's perfect. Then, oh yeah, and also we'll install the 1.1.0 B0. Good. Time to continue this. This we called membrane packing.mend. We pack it and then we render it. And we solvate it. Pack, render, and solvate. And that should be it. And then the cool thing is we can actually also, so then we say, do some MD. If that also works nicely, then we're very happy. Let's do it with this one. Great. Now I want to consider, do I actually want some nice... I don't generally love stuff like this, but it's helpful here, I think, to actually have some organization in that way. Cool. Let's fix up these. We need to do, I need to get that into that, and then we go up to EOF like this. That should do it. It's probably still wrong in some way. Let's make a nice user bin bash or user bin env bash, whatever. I'm sorry, I'm distracted by texts, as always. Yeah, and then we want to set XEUO pipe fail, which makes us happy. Then we can go. Let's try it. Wait, that's not what I want. Did we call it tutorial? Something. Oh wait, it's not located here. It's located here. Yeah, let's also tag our release here. Wait, what's our tagging strategy? Yeah, it's a Rust version. So git tag annotate 1.0.0 data 0. Heading toward 1.0. Very nice. And also let's upload our release to PyPy, because we only have it on test PyPy. Perfect. So now, within foreseeable time, we should be able to do our tutorial integration. Yeah, that's literally the worst. We're going to add this. Still quite cross about that, but whatever. Yeah, this is not my problem, because I've been asking for my dear friend Bart to fix this, but this should work. Cool. It doesn't work. What's happening? Oh, interesting. Of course, those comments are actually not valid because they are behind a backslash. And topo.top. Let's check for some more comments like this. Yeah, so we should remove this and this. I mean, here they actually don't matter, so might as well leave them in. So these are actually, that's like a pandoc thing where I can make the nice circled number things happen in the files, but in the code listings. Closing, yeah, that's a very good point. See, I keep forgetting that because I know I will change it, but that should do it. I think it's working. I think it's working. And then something went wrong. Oh, that's very nice and interesting, because when you use this good practice thing, GrowMax cannot be sourced properly. So we need to first turn that off and then turn it on again. Maybe, yeah. Or we can just run it in a local shell. No, this is okay. We can just do this. There we go. Energy minimizing. And now we do an equilibration. can actually look at the results, and then I can show you why it's also wrong. We need to change something else. But I don't know exactly where I need to do that. Let's actually see what the diff here is on the... Hey, what the fuck? Please. Oh, it doesn't recognize it. Okay, that's fine. Jesus, why can't I... That's the important bit. The whatever. It's crazy. I actually rewrote so much of it. I mean, content-wise, it's quite similar, but the almost everything has been touched. That's honestly crazy. This took so much work. Jan has also done such a good job with the initial tutorial. I mean, I contributed to that, but Jan really pulled that effort and did such a good job, and that really made it so much easier for me to now make a good updated tutorial. So I'm very thankful for that. Now it's already doing the production run. So we can actually start to investigate that. So let's go into temp. Let's see. Let's look at what the latest one is. I forgot to note what it is, but I think it's here. Perfect. So now we can vmd em.grow eq.ecstasy. So now we can look at what the trajectory is for the equilibration, which, I mean, shrinks a bit. What you notice now, it's a nice cube. And now it's already starting to like elongate a little bit. I don't know whether that's noticeable so much. I think I can see it. That's very short. And now we can load eq.grow and then md.ecstasy. I don't think it's writing out too many frames, but there should be, it's nothing yet actually. Yeah, that may take a bit, but anyway, the simulation is running, which is good. Yeah, but let's stop this because this will otherwise finish on fucking Sunday, so let's not do that. Cool. That's very bad performance. Why is that? Anyway, yeah. Okay, so now we also have a cool test. We found something interesting, which is that, once again, MDV containment 2.0 is posing a problem for us. Let's look at the PyPy. Yeah, okay, so I'm just going to shoot our dear Bart a message that he really needs to do this. I'll just leave it there. I need to hop off now, but yeah, sure.